Hello, in this short presentation I would like to introduce some of the fundamental challenges associated with a culture of safety that is spanning across the entire workflow. Important needs will be identified and potential solutions to key challenges proposed. Providing a safe and healthy workplace is a core responsibility for every employer and a business priority across the high-value chemical industry. Often products are developed and produced under extreme conditions. Therefore, the chemistry, the process and its risks must be clearly understood to ensure safe and compliant operation. Regulatory bodies, for example the OSHA in the US, HSC in the UK, the European Agency for Safety and Health at Work in Europe, or the State Administration of Work Safety in China, are driving these regulations to improve the safety in the industry, leading to improved personal safety at the workplace. HSC EHS aims to reduce work-related injuries, deaths and illnesses and focuses on health, safety and environmental considerations. Chemical development often is a hands-on activity in which many steps are manual. Therefore, the exposure to toxic and hazardous materials is a risk that must be addressed. Minimizing the use of dangerous solvents and reagents can help as well as protecting the researchers. So can automation of manual tasks associated with experimental execution too. Complete understanding and careful designing of hazardous processes minimizes the risks and prevents accidents. High-risk processes and related designs must be assessed for safety under challenging timelines with small amounts of chemicals very often. In that case, the criticality of the material needs to be investigated first, and the full safety assessment is postponed until after key decisions often have been made and are difficult to change afterwards. Scientists can evaluate safety concerns earlier in the development cycle, but it can be challenging to obtain critical information with only limited material. Environmentally friendly processes, green chemistry, waste management, but also preserving energy and resources are one of the major challenges when new products and processes are developed and introduced. In the context of the culture of safety, the most important question to ask is, can the three aspects, personal health, product and process safety, as well as environmental safety, be united? It is for sure everybody's company's and labs person's interest to overcome the challenges of personal safety in the chemical and process development. And of course, also to make research environment as safe as possible. Or with other words, monitoring processes carefully, ensuring reactions and process conditions are chosen safely, and trying to avoid exposure to unsafe chemistries as much as possible are everyone's responsibility. However, it is no question that these days processes can't be introduced without identifying the non-scalable conditions, the exothermicity of a process, or the understanding of the impact of the critical process parameters on the process itself. In many cases, the availability of limited amounts of material is a challenge in itself, and the equipment used for the development as well. While considerations on safety comprise product as well as process safety, we will focus mainly on reaction safety. An ever-increasing pressure due to environmental consideration forces companies to focus to reduce their impact on the environment. This includes not just reducing the amount of waste, but also to better understand non-toxic alternatives to existing chemicals and products, improving the energy and resource efficiency, as well as the collaboration with regulatory bodies. Now, let's first look into the needs and challenges that are presented when looking for a safe workplace. Exposure to harmful substances is among the 5 most common causes of workplace injuries in the chemical and pharmaceutical industry. Typically, traditional tools or principles of operation do not inherently protect the users sufficiently. Limitations are on the one hand the risk due to toxic and dangerous components, but on the other hand also the apparatus and equipment used. So for example, taking samples from reactions can be a safety risk due to high temperatures, a pressurized reactor, boiling conditions or the like. Even dealing with liquid nitrogen or dry as acetone may pose a risk or is even not permitted in some labs. Operating modern equipment is designed to protect the operator, while traditional lab equipment such as round bottom flasks or similar poses the risk of injuries, for example burns of skins, spillages of hot liquid or gases, cuts due to broken glassware or stitches because of needles. However, please keep in mind that even the way in which processes are carried out can pose a risk. So, what are the considerations when it comes to personal safety or health? Highest priority must be given to safe setups, the control of reactions, and online analytics. So it is evident to manage the challenges provided by the possible risk of injuries and remove the typical fume hood hazards, eliminate exposure to chemicals or liquid nitrogen, minimizing tripping hazards or precarious setups. On the other hand, a tight control of the reaction with a powerful and automated workstation that can be operated from outside the fume hood enables that also fast and strong reactions can be kept under control. And last but not least, the risks associated with sampling must be eliminated, limiting the exposure to chemistries, and at the same time measures must be taken to ensure safe monitoring of reactions occurring under extreme conditions. For this reason, a precise and reliable personal safety toolbox, including an easy to operate and accurately controlled automated reactor workstation, must be employed together with seamlessly integrated reaction monitoring equipment. It is therefore important that the experiments are carried out accurately and reproducibly, while at the same time consistent data is generated and stored. The Shell Technology Center in Hamburg is a great example of how experiments are carried out safely and reliably with the maximum safety for the researchers. The React IR 702L resolves multiple challenges for them. Applying reaction monitoring in both lab and plant online. It's easy to operate and reliable in process monitoring. It offers a maximum personal safety as no liquid nitrogen is required, which is prohibited anyway unless protective clothing is worn. For the researchers in process R&D at Grünenthal, it is important that the experiments are run safely and without manual supervision in order to increase productivity without increasing staff. A challenge in this scale-up was a process step within a Grignard reaction. The highly exotherm reaction and the limited heat removal capabilities required reagent dosing times between 8 and 16 hours. Such long execution times for dosing exceeds the length of a normal scientist's working day. A solution was needed in order to leave the dosing running unattended, even overnight, without violating any safety guidelines. This challenge led the process R&D team to choose a plug-and-play reactor control solution called the RX10 to automate temperature control and semi-batch dosing to run the highly exothermic reaction unattended and without making compromises on safety. Determining profiles of the starting material, the formation of products or impurities, is most evident if reaction needs to be tracked, and recording of sampling times for overlay and reporting with online data, for example hydrogen uptake, calorimetric data, provides the researcher most valuable information. However, only reproducible sampling allows quantitative determination of yield, kinetics, and impurity profiles. Manual sampling of reaction mixtures may be difficult, unreliable, and is typically a risk as the researcher can be exposed to toxic or dangerous products. When reactions are carried out under pressure or vacuum, boiling conditions, or the reaction masses are prone to humidity or air, sampling may be difficult or even impossible. However, taking samples with an automated programmable sampling device does not just eliminate the risk due to needles, vapors, or spilled liquid. It also ensures user safety at any time, for example, no leakage of hydrogen out of the reactor, no leakage of air into the reaction, and so forth. One of the consequences of attempting to address chemical reaction hazards at a very early stage in R&D is that the scientists may not have a true knowledge of how much heat may be generated in a reaction or how stable a particular raw material or reaction mixture may be. The aspect of proton process safety is therefore one of the key elements whenever a chemical process is scaled from lab to production. The safe scaling of a process from laboratory to production requires a high degree of expertise and the respective equipment to achieve the goals of a safe, economical and ecological manufacturing process. Unfortunately, incidents and accidents in the chemical and pharmaceutical industry still happen too frequent and often have serious consequences. These can be minor or major damages to the plant, leakages or spillages of chemicals and solvents that cause damages to the environment and or poison or injure people, explosions and fires with injured or dead people, complete destruction of manufacturing areas with catastrophic consequences for people and neighborhood, and many more. The causes of incidents can be manifold, but often are related to malfunction of equipment, insufficient or wrong mechanical plant design, broken pipes, overpressure, leaking vessels, blocked pipes, corroded valves, and similar things. Human errors, faulty operation, as well as loss of control are causes of incidents as well. On the other hand, incidents are frequently related to insufficient knowledge of the chemistries or the process, and sometimes also the products itself. Bad data or information, or taking wrong conclusions from the information that was obtained. However, the loss of control always has catastrophic consequences. In our discussion, we will focus on three areas: the impact of the parameters on the process, the potential risks that are associated with, and the what-if scenarios that we will look into. Considerations on safety require in-depth understanding of the reaction conditions and the kinetics of the reaction. In addition to the obvious, it is essential to take plant-related aspects into consideration as well, which for example take considerations interactions of intermediates and products with the plant material into account. However, one of the crucial and often unknown impact are limitations to heat exchange. These can be manifold and include the impact due to increasing viscosity, fouling, or simply the fact that the ratio of the volume versus heat exchange area gets less the larger reactor becomes. When scaling reactions from the lab to pilot or plant scale, frequently observed effects become important or even a threat. Delayed or auto-catalyzed reactions may lead to accumulation of reactant and or heat, resulting in a temperature increase of the reaction mass, followed by side reactions or even decomposition. Consequently, the reaction mass temperature may increase further, leading to runaway reactions and resulting in a worst case situation, which may be an explosion. In some cases, reactions involve gases or are accompanied by gas evolution, for example during chlorinations, brominations, decarboxylations, decarbonylations, etc. etc. These gases need to be removed in a controlled manner in order not to build up pressure, which may harm the reactor or its installations. Based on the acquired knowledge, the situations can be analyzed and the corresponding what-if scenarios developed. Typical scenarios, for example, are: what happens if cooling fails? When is cooling failure the worst? What if we lose power? What if mixing and cooling fails? And much more similar things. The answer to all of these questions will help to define the best process parameters and to identify the corresponding measures to be implemented to ensure the process can be run safely. To help identifying the relevant parameters and the possible impact of a change to these parameters, we have developed a toolbox to explore the desired and the potentially undesired reaction. These include reaction calorimeters, analytical tools such as in situ spectroscopy and automated sampling to follow the progress of the reaction, differential scanning calorimetry, as well as IC safety software to estimate the criticality of a reaction. Continuous monitoring of the reaction mixture provides details about the presence of reactants, intermediates and products online. In the case of a Grignard reaction, which is presented here, the reaction control and monitoring workstation, a combination of the reaction calorimeter RC1 and reaction monitoring tool React-IR, are the key technologies to monitor and follow the progress of the reaction. The key challenges of such reactions are that the tracking of start and progress of the reaction material are difficult. The reaction may not initiate or stall, which accumulates halide with a potential for a runaway, or the halide is not consumed at the rate of addition. By overlaying React-IR and RC1 data, the consumption of the halide can be tracked and the heat flow identified at the same time. This allows to understand the impact of accumulation on the reaction progress and to identify the best possible addition rate to scale the reaction safely. One of the risks of many reactions or processes is the fact that the reaction doesn't initiate together with the addition and accumulates a reactant, or the heat production is larger than the heat removal capacity of the system and the system accumulates heat with a subsequent increase of temperature. Therefore, the scientists often face challenges like the accumulation of reactants or energy is not clearly understood, which may result in a wrong decision or may require large safety margins at plant scale, insufficient cooling at large scale, which may lead to an increase of temperature or even worse to decomposition of the reaction mixture followed by a runaway reaction. With other words, scaling reactions from lab to pilot or manufacturing scale requires to understand all aspects of the impact of temperature, dosing rate, or other parameters on the progress of the reaction, the heat of the reaction, the heat transfer, mixing and mass transfer, etc. In the case present, the reactant doesn't react instantaneously with the addition, and the majority is accumulated over the time of addition. The reaction only initiates slowly, becoming very strong shortly afterwards. Once the reaction is started, it releases a large amount of heat in a short period of time, leading to a substantial temperature increase. In case the reaction mixture would decompose at elevated temperature, the process would be prone to a secondary reaction followed by a runaway reaction. With the algorithms and evaluation capabilities built into iControl software, only the RC1 reaction calorimeter is able to accurately determine the true heat of reaction and other relevant parameters, making sure all information is accurate and understood well. Interpretation of safety-related data might be challenging, and there is always the question, how does the quality of data relate to the safety of a process? Or, to phrase it differently, what are the consequences of bad or incomplete data? In order to confidently bring a process from lab to pilot or manufacturing plant, the data quality must be sufficiently high and accurate and reproducible. However, data always have errors which may be smaller or larger depending on how they were determined. As a result, the uncertainty in the data sets require that a safety margin must be applied when a process is set in place, else there may be a risk for incidents. With increasing uncertainty, the risk of wrong decisions increases. As a consequence, the safety margin will need to be increased as well, which makes the process more costly and less efficient. Well, the third pillar to establish a culture of safety are environmental considerations that are an integral part of today's development process. The environment may be impacted because of the nature of the products, incidents, accidents, or simply due to the wasting of resources. By making processes and businesses eco-friendly, both the environment as well as the business itself benefits. However, the challenges are not always easy to overcome in order to stay competitive in the market. Often it is the structure of the organization, the process itself, or the age of the plants that may make it difficult to reduce the consumption of energy, or more generally, to reduce the waste of resources. Many processes are in place for years, developed with tools and capabilities of the past and thus not optimal. This may result in an unnecessary consumption of chemicals and solvents, or produce byproducts that need to be eliminated at a later stage, consuming additional resources. Also, additives that are added to the consumer products or degradation of disposed consumables pose a threat to the environment that needs to be reduced or eliminated. In fact, the impact of our business activities on the environment is complex and very diverse. Therefore, in this presentation we will focus on the development cycle and in particular on consuming less chemicals, creating safer materials, and the efficient use of energy in development. During the various stages of the development workflow, one often faces the challenge of how can we reduce the number of experiments to use less material. This inherently means to reduce the number of repeat experiments, the number of failed experiments because of unreasonable reaction conditions, the lack of sufficient experimental data, or the lack of sufficient accurate control of the experiments. Environmentally harmful or toxic starting materials often have alternatives that need to be identified and tested. The challenge of the past might have been that corresponding monitoring tools were missing, or monitoring and control of hazardous byproducts was impossible. Using energy efficiently or reducing energy consumption in development process is a challenge that can be tackled and also achieved by using the right tools. But what about understanding the progress of the reaction to stop it at the right time? Will this not also allow to save energy and resources, or maybe even bring some economical benefits for the company? To tackle the challenges discussed just before, an efficient, integrated and accurately operating toolbox is required that can help resolving the issues of reducing the consumption of chemicals and solvents, ensure consistent and reproducible processes, as well as monitoring process and products. Obtaining the relevant data with as few experiments as possible is one of the challenges that can be tackled with modern techniques and tools. For the development of new products and processes these days, the technique of design of experiments is often applied successfully. In a DOE, multiple parameters are varied at the same time based on a statistical approach. The key to a successful and efficient DOE, however, is that the manipulated parameters can be reached accurately and controlled precisely. The synthesis workstation EasyMax ensures that parameters such as temperature, stirring speed, dosing, pH, etc. can be controlled precisely and the data are recorded consistently. If required, it also can be equipped with a sampling or monitoring tool such as an easy sampler, an infrared or Raman system for additional information. Consequently, the development can be done with fewer failed and repeat experiments, with improved quality, using less resources, and last but not least, also more efficiently. As isocyanates are a serious threat to humans and the environment, their residual concentration in products is regulated by the EPA. Understanding the mechanism, the kinetics and the progress of the reaction is thus key for fast understanding of the degree of polymerization and the residual starting material. React-IR enables manufacturers and formulators to ensure that product quality specifications, personal safety and environmental regulations are met. By looking at the polyol and pre-polymer product in this application example, we see that the reaction ends shortly after 3 hours. The trends indicate, though, that the diisocyanate doesn't reach zero. This is because the functional group is part of both the reactant and therefore also the final product. This information allows the scientist to confirm to the manufacturing group the necessary information to monitor and correct deviations to avoid creation of unnecessary diisocyanates and subsequently unusable batches. By monitoring the consumption of energy, in many cases the aspect of ecology and economy can be tackled jointly. AstraZeneca, for example, investigated the energy consumption, so the electricity, of their traditional development tools like the round bottom flask and JLRs heated and cooled by cryostats or thermostats, and compared that to the synthesis workstation of EasyMax and Optimax. Now, replacing the traditionally used cryostats and circulators with EasyMax and Optimaxes, AstraZeneca was able to save energy and significantly reduce the cost, which is around £8,000 per lab and per year, due to the more effective heating and cooling of the synthesis workstations. At the same time, the aspect of more accurate and reproducible experiments applies additionally, which reduces the use of chemicals and solvents too. So, how does the culture of safety impact the business overall? First, by improving the personal safety in the lab, the working environment becomes more healthy, resulting in less time out because of injuries or illnesses. Secondly, investigating the product properties and understanding the risks and criticality of processes leads to more efficient and safer processes that are robust and ensure an economic and ecological manufacturing of intermediates and products throughout the product chain. An aspect that can't be underestimated is the fact that incidents in production of chemical and pharmaceutical products often impact the reputation of a company, which is an important factor to consider as well. And thirdly, energy, resource and waste management and sustainable processes will not just benefit the environment, but also reflect in the company's success, both financially and in the reputation. Now, you can find a couple of citations and references on our homepage under www.mt.com/ac-culture of safety.